This next section of our notes deals with trig identities. And what is a trig identity? It is an equation involving trig functions that's always true. And there's lots of them. You already know a couple of them. For example, I'll just open that up. These are the ones that we know already. From your big ideas from chapter 6, what is tan theta always equal to? Sine over cos. That is considered an identity. Because you have one trig equation equal to another trig equation. That is always true. We also learned from our big ideas that this is always equal to 1. That is an identity. Did I give you guys formula sheets here? Yes. We're going to use, there's going to be a lot. So in chapter 6, there's like two formulas on your formula sheet. The sine squared theta plus cos squared theta equals 1 is on there. And your arc length formula, S equals theta r. Then basically the rest of the first column is all of chapter 7 formulas. So there's a ton of formulas that we're going to have that are identities formulas. But to start off with, these are other mini identities you have already learned. You know that cosecant theta is 1 over sine theta. You know secant theta is 1 over cos theta. You know cotangent theta is 1 over tangent theta. And because you know those, the flips are also true. You know that sine of theta is 1 over cosecant theta. Cos of theta is 1 over secant theta. And tan of theta is 1 over cotangent of theta. You also have our big identity, we wrote it down before. Tan of theta is sine theta over cos theta, which means that cotangent theta, being the reciprocal of tan, is always cos theta over sine of theta. Good day, sir. Awesome. Now, I'm going to introduce you to our first main strategy. Our main strategy, there are 6 trig functions: sine, cos, tan, and the reciprocals, cosecant, secant, cotangent. But based on these big ideas, you could change everything to be either sine or cosine. I'm gonna circle it with a green box here. For example, if you have a cosecant, you could change it to be 1 over sine. And then you wouldn't have cosecant anymore. If you had secant, you could change it to 1 over cos. And then you wouldn't have secant anymore. If you had tangent, you could change it to sine theta over cos theta. And you wouldn't have tangent anymore. And if you had cotangent, you could change it to cos theta over sine theta, and you wouldn't have cotangent anymore. So this is going to be one of our first main strategies we're going to use in this unit. From here, you could, if you wanted to, take any equation and just use sine and cosine. You don't have to worry about tangent anymore. Don't like tangent? Change it to sine theta over cos theta. Don't like cotangent? Change it to cos theta over sine theta. Okay, now I handed out a paper to you guys, and I'm going to introduce you to trig identity proofs. So a bunch of this unit is going to have questions that are going to say prove, and on your identity sheet that I just handed out, on the side that has 47 questions, well, it doesn't actually have 47 because it starts with 5, and it skips some other numbers. But if we look at number 5, you will get questions like this. Prove, and this question has cos t secant t equals 1. And there is some important formatting things that come up with proofs. They're trying to tell us this is always true. Anytime you have cos, like if I do cos of 13 degrees times secant of 13 degrees, the answer is always 1. This is a new identity, and they want you to prove the identity. So the way that we prove identities, first a couple of formalities. We need to split up the left side and the right side. So the first thing we do is we draw a line where the equal sign is. And you should do these on a separate piece of paper. So if you need loose leaf, I have extra loose leaf. Here, I'll start it. If you want loose leaf for this, grab some, pass it on. I'll do half here. We'll do half starting over here. And at the beginning, we only have one strategy so far. We'll end up with like 8 to 10 strategies in the end. But to start off, here's our main strategy. Change everything to sine and cosine. And then you're going to use your fraction rules to figure things out. Okay. So in this question, what a proof is basically a puzzle. You're allowed to manipulate on the left side. You're allowed to manipulate on the right side. In the end, you want the left side and the right side to be exactly the same. And we're going to use the main strategy of changing everything to sine and cosine. So, will I change cosine? No, it's already cosine. So I'm going to rewrite it. Cos of t. Can I change secant of t to sine and cosine? Yes. What is secant of t equal to? It's equal to 1 over sine or cos?
Cos.
1 over cos. So there's step 1. I change the secant t to 1 over cos t. Now I'm multiplying fractions. Basically, that's like over 1. How do you multiply fractions? You multiply the top, you multiply the bottom. Can you simplify? Can you see that this cos t and this cos t would cancel out and just become 1? And we finish the puzzle. Now the left side and the right side are identical. So we add a little statement that says the left side equals the right side.
What's the
Okay.
3 dots?
3 dots is short form. Does anybody know what is short form?
Therefore,
No, there's 3 dots. I'm kidding. It does mean therefore. It's such a mean thing to say. I know, but I can't help it. It's like there's 3 dots. Therefore, no, 3. Yeah, it means therefore. I don't know, mathematicians. This is a shortcut for this word. Therefore, the left side equals the right side. And then, for me personally, a lot of mathematical proofs end with QED. And then I always add a little box with some shading, because it's something I did in university and I still do it. Okay. QED is an abbreviation. And each of those three words are in Latin. Any guesses? No, probably not. Okay. It's Latin for, well, you won't know if I pronounce Latin wrong, so I'll just wing it. Quod erat demonstratum, which directly translates what was asked for has been demonstrated. Sounds pretty impressive. So, a lot of mathematical proofs in textbooks, when they're done, they write QED so that when you're reading it, you'd be like, oh, it's done. Because I didn't understand any of that. It's usually, oh, we finished. That's what happens in higher level textbooks. You look at something, you're like, oh, I have no idea what was going on, but I guess they're finished. And now I should reread that 5 more times to see if I can figure out what happened. And then sometimes textbooks have a little symbol added. You can make a little smiley. You can make your own symbol up. I always did a little box with shading. That's my own touch. You don't have to do the little box. You don't have to do the QED, but you do have to make this statement. But if you want to add the Latin, just a nice little touch. Okay, this is a proof. We draw a line. If you make an equal sign in your equation before you proved it, it's an automatic 1 mark deduction. Because you do not know that they're equal until you've proven it. So saying they're equal before you've proven something is a 1 mark deduction. So the first thing we do is we draw the line to separate. This is the left side of your equation. This is the right side of your equation. Our goal is to manipulate the sides until they're the same, and then we're done. So, it doesn't mean anything. It's just like,
Why you ever added
so the little symbol just has a way of saying that it's ended. If you would look at magazine articles, sometimes magazines have their own little symbol to end an article. How often do you look at a magazine? Probably not very much anymore because everything's online on your phone for reading articles. But it used to be that if you would read an article, you would get, say, a Maclean's magazine, and you were reading an article. They actually have a little maple leaf with an M in it when the article ends. And one of the reasons they do that is magazines were full of advertisements. So you'd like read 1 page and then you'd have to flip 3 pages later, and then the article would continue. And they would put the little symbol to tell you, we're actually done now. So the little symbol has been used in a bunch of different ways just to represent a finish. Okay? Yeah, I should see one of my university. See if this one has any proofs in here and symbols that they used at the end. No, this one doesn't have. But I had it in some of my university texts that would have little symbols at the end to say the proof is done. Question?
Should we just put 1 on, can you put 1 on the other side? On the right side of the equation?
It's there already. By drawing the line, everything that's above.
Okay, but you wouldn't be wrong if you put
You wrote another 1 there is fine. Yeah. Okay, next on your page, we are going to do another good one to do next is, let's do number 8. So I have prove. So the first thing you would often do is you rewrite the question. Prove sine x secant x equals tan x. Then draw your line to make sure you don't skip from left side to right side. You are never allowed. Sometimes you might be very tempted to take something from the left side and do algebra and move it to the right side. That line is like a wall. You're not allowed to move things from left side to right side. As soon as you do that, the marking stops on the question and they just sort of say no more marks for you.
Will you ever be asked to prove something that isn't possible?
No. So if on the exam it says prove, it is possible. If it's not working for you, you are making mistakes somewhere. And it can be terribly frustrating when you make mistakes. Because you're like, it's not working out. The first time you make a mistake, they deduct 1 mark. If you make a mistake to undo your mistake, to try to make it work, you lose another mark for making the next mistake. So, if it's not working, usually it's better just to stop.
Start again.
Rather than making up new math to try to fix it, could be a problem. Okay? You can't also do stuff like this. I have no idea, so I'll just write 10. Look, they're the same. I'm done. I'm amazing. The left side and the right side are the same. Okay? There was a student on a final exam who did that. With the underneath here, they wrote the following. Ladies and gentlemen, it is obvious that sine x secant x equals tan x. No works needs to be shown. Left side equals right side, QED, I'm done. No, you do have to show work. So they would get no marks for just, right? But it's tempting. Things aren't working. You're like, maybe they won't notice. Don't do that. Because it's the job of this unit to notice all the details. So we use the strategy. I can keep sine x the way that it is. But I can change secant x. Secant x is 1 over cos x. So this would be multiply the tops, multiply the bottoms, because that's a fraction though. This side is now a single fraction. Sine x over cos x. I look at the right side. They're not equal yet, but they're close. So you have options here. Some people will change this left side, and can you see that big idea? What's sine x over cos x? It's tan x. Some people will change this to tan x. Some people will say this side is sine x over cos x. And once they're the same, the left side is equal to the right side, so QED. Very nice. We are all done. This is the idea of proofs. The first ones up to 14 are really straightforward. And then they get more and more complicated. In fact, we have to add more and more strategies. Yeah. Okay, let's do one more together. Let's do number 14. Because it involves adding fractions and fractions inside of fractions. So I'll start by, this was the original question. Prove sine u over cosecant u plus, and there was a typo here, cos u over secant u equals 1. Draw the line. Using the main strategy. And have sine u over, what can I change cosecant u to? 1 over sine u. Plus cos u over, and I could change secant u to 1 over cos u. And now I have fractions inside of fractions. How do you do sine u divided by 1 over sine u? Well, the top technically is a fraction, right? This is sine u over 1. And this is technically a fraction over 1. How do you do a fraction divided by a fraction? You multiply by the reciprocal. So I flip the second one. Same thing here. Multiply by the reciprocal. So a lot of times in proofs, you're just going to do fraction rules for a long time until you've simplified your expression. And what is sine u times sine u? That's sine squared u. And cos u times cos u, that would be cos squared u. All right. What should I do next? Well, they're not the same yet, they're close. So we can't say left side equals right side until they're identical. So you would have to, you're right, there's nothing, this is equal to 1. So I have to write 1, now that they're the same, I can say left side equals right side. Oh, let's get fancy. Yes.
So do you always have to write the therefore part, or can you choose like one or the other?
You have to write this part. Yes.
Okay, so you have to write that part. You
Yeah.
can write both. You don't have to write the Q.
You don't have to write the QED, but it's super enjoyable. So
Super enjoyable.
super enjoyable. One kid asked, like, because now I get fun. I had fun with it. Student once asked, "How do you know? Like, you keep changing the font, making it big letters, little like." No, I'm just having fun. I don't have a calligraphy pen. That's okay. Question.
Do you lose mark if you get the dot, the therefore dot?
If you don't make the statement that you notice that they're the same, yes.
Can you say therefore instead of 3 dots?
Yeah. All right. So